Hello everyone. This video is about common emitter amplifier. Common emitter amplifier is a bipolar junction transistor-based amplifier with the emitter sorted to the ground. To begin with, I would like to show you an example how the common emitter amplifiers look like. The simplest form is like what is shown in here. You have a transistor and the base is connected to the ground and the voltage at the output is to be tapped here. And the input is to be fed from the B terminal, directly or indirectly. So in our case, in this example, we are trying to make things simple. The base terminal is to be biased with a voltage V, no, and on the top of the DC voltage, there is a small signal, not small signal AC voltage, V in, and this is example 1. So to analyze the circuits, the first thing that you need is to replace the transistor with the small signal equivalence. So step 1, replace all the BJT with their small signal equivalent. So in here, according to the circuit, we have one BJT here, and this BJT is to be replaced. So let's start from here. We have a, by the way, it's easier to go through all the procedure first. Step 2. So whenever you come across with an independent DC voltage, like what is shown here, VCC. VCC is an independent DC voltage source. And another DC voltage source is V out, V naught here. So short circuit or the DC independent DC voltage source, sorry. Independent DC voltage sources. Step 3 is to open circuit. Or the independent current source. Independent DC current source. And finally, you just resolve the circuit like what you did in Teflon and Lawton analysis. In this example, the transistor here is going to be replaced with what we have learned, the pi model. The next step is to short circuit the uh, independent voltage, independent DC voltage source. And this one is going to be AC ground, and this one is going to be grounded. So in this case, we have a output terminal here, and then this one is connected through a resistor, and this one is connected to ground. R1, R3, sorry. And at the output, this one is going to be invisible in a small signal analysis. And the input needs to be connected to the small signal input in, and there is no V0 in the equivalent circuits, because this one is going to be short circuits to the ground, to the AC ground. Now, with this in mind, we can resolve the circuit quickly. My approach is to start with the small signal collector column, IC. Here, IC is equals to Gm V pi, and according to this network here, IC is equals to minus V0, V out divided by RC, while in this this one here, V pi is what is actually the input voltage, V in. So by direct observation, we can quickly find out the voltage gain. The voltage gain, let me check if we have enough space here. Apparently we have. So the voltage gain, V is equals to V out divided by V in, which is also equals to minus GMRC. So this is a very simple example. You may be interested in the input resistance as well. The input resistance is normally cut from this point onwards. And by direct observation, RE is equals to R pi. There's nothing difficult in this example. Now, the problem is, in this circuit topology, you may notice we have two independent DC voltage sources. One is VCC, another is V0. We don't want these bulky items. Too many bulky items in the circuit is not going to be good for the cost. And on the other hand, it's not that easy to apply the small signal AC here. At least we cannot do it directly. It's not easy to do it directly here. So in example 2, I'm going to show you a more realistic common emitter amplifier. So example number 2. Basically, the circuit is very similar. At the output, we have the RC here, and we are going to short the emitter to the ground. And normally, the output voltage is to be tapped directly from, indirectly from here, rather than directly. If you do that, you tap the voltage at the output directly at this point, you will also pick up the DC voltage. So we don't want the DC voltage at the output. So what we can do is to use the capacitor to filter off all the DC voltage. And at the end, on the right side of the capacitor, you will have only V out, the output voltage left. And the input is to be fed to the B terminal. And the way how we are connected here is uh, not quite practical. So what we don't normally do is to build the biasing network based on the same voltage, VCC. And we use the voltage divider technique to handle the DC biasing. At the input, we are going to fed the signal through this point here. And the way how we do it is to use the capacitor again in the very similar manner as this one too. And the reason we need the capacitor is to filter off all the DC signal. And we are going to do this. And then this is C1 and this is C2, and the input is going to be in. So this is the more realistic common emitter amplifier. The only difference between this one and the previous one is the biasing level and also the capacitor. So to analyze this circuit, we can follow the similar procedures. First, we start from step one and replace all the bipolar junction transistor with the small signals equivalent models. So we have only one transistor here. All we can do is to use an equivalent circuit model here, like this one here. So this is the same model as we did before. So the next step is to sort all the independent DC voltage sources to the AC ground, and like this one here is going to be sorted, and this is apparently the only independent DC source here. Now, with this in mind and the output here has a capacitor. Capacitor is conducting to AC. So it will appear like a straight conducting wire with very low impedance. The output resistance will be connected in here and RC, and here is the output. The input at this point, which is equivalent to the B terminal here. And B terminal here is connected to resistor R1 and R2. And resistor R1 is connected to the VCC. VCC is equivalent to a ground. So eventually, this VCC AC ground is not very much different from the physical ground that we have here. So what we can do is sort these two together and connect them to the ground. So the step number 2, and this one is R1 in parallel with R2. The input at this point B has the input signal, and the input signal is to be applied through the capacitor C1 here. In high frequency, this C1 is conducting to AC currents. So in other words, we can just show it is a straight wire with very low impedance, and the voltage source at the input is V in. And step 3, open circuit all the independent DC current sources. We don't have any independent DC current source here, so we just ignore it. We solve the circuit, and this is the final step. My normal approach is to start from the small signal collector current. I see here. IC in this case is equals to Gm pi, and again we can replace IC with minus V naught divided by RC, and the right side of the equation is Gm times V pi. V pi is the voltage across this resistor. By direct observation, we know that V pi is just V in. So, just like the previous example, the voltage gain is going to be equal to minus Gm times RC. And you may be interested in the input impedance here. And the input impedance in this case is these three resistors in parallel. So Rin is equal to R1 in parallel with R2 in parallel with R pi. What else? I think this is almost done. If you are asked to calculate the current gain, we can just treat IC as the output current, and the input current is going to be voltage divided by this one. So if you want me to show you the current gain, it's easy. So first of all, we are going to free up some space here. The output current is equal to IC, actually minus IC, because we want the current to count from here. The input current is going to be this voltage divided by the input impedance. And V in divided by R in, according to the equation here, is R1, R2, and then R pi. So if you do it carefully, by the way, IC, you can quickly find out it is VL divided by RC, okay? Yeah, you can use plus here, okay? So now the current gain is IR divided by IE, and this one divided by this one. So eventually you will end up with V out, V in, R pi divided by RC. We have already worked out the voltage gain here. Yeah, the voltage gain is equal to V in over V out. Sorry, V out over V in. If this is the case, you can just substitute this expression into the final expression here. So minus GMRC. So this is number 1 point. And then we need to, because this is minus. Yeah, we have a minus here, sorry about that. So we have a plus here, and then times this trunk of expression. Pi divided by RC. So this is the current source, the current gain of the amplifier. If you have any questions, please leave your questions to the comments box. If we have time, we will deal with your questions. Thank you very much for attending this module. Thank you very much for attending this lessons.